Today I'm introducing one of the most important concepts in number theory. It's called modular congruences. So the definition of modular congruences is that we say A and B are congruent and M if M divides A minus B, then A is congruent to B mod M. So, for example, let's say 10 minus 2 equals to 8, and 4 divides 8. So you can make 10 is congruent to 2 mod 4, because 10 minus 2 is divisible by 4. So this basically what congruence means. But this has many important properties that we can use to deal with problems. So first, let's look at some propositions. Note that we denote this symbol as congruences. So let's look at proposition. The first one is A is congruent to A itself mod M. The second one is if A is congruent to B mod M, then B is congruent to A mod M. So next, if A is congruent to B mod M, B is congruent to C mod M, then A is congruent to C mod M. So now we can say that A is congruent to B and is congruent to C mod M. Next one, if AI is congruent to BI mod M, then A1 plus A2 until AN is congruent to B1 plus B2 until BN mod M. So each individual for A1 minus B1, A1 is congruent to B1 mod M. So when they add together, they are also can be divisible by M. Fifth, if A is congruent to B mod M, then A plus C is congruent to B plus C mod M. This means that if you add numbers for congruences, this is true. The sixth one is similar as the fourth one. So when you times them together, it is also true. Seventh is the same as the fifth one. Like if you times another number, that is also true. Next one, if A is congruent to B mod M, then the greatest common divisor of A and M is equals to the greatest common divisor of B of M. The last one, if A is congruent to B mod M, then A to the N is congruent to B to the N mod M. So A to the N minus B to the N, we know that this is divisible by A minus B. So this is definitely true. Thus, we see that some common properties between A and B and M. And now let's see some problems by using these propositions. The first one is to prove that 13 divides 2 to the 90 plus 3 to the 90. So I didn't put this question under the divisibility topic because this can be solved by congruences easily. So first, you look at 13. 13 equals to 4 plus 9, which is 2 squared plus 3 squared. Thus, we know 2 squared is congruent to negative 3 squared mod 13, which means that 2 squared minus negative 3 squared is divisible by 13. That's 4, and minus negative 9, which is plus 9, and that's 13. 13 is divisible by 13. So we change that to the modular congruences. Now we know that a to the n is congruent to b to the n mod m if a is congruent to b mod m. Thus, for 2 to the 90, this is 2 squared to the 45th, and 3 to the 90 is 3 squared to the 45th. Thus, it's negative 3 squared, all of them to the 45th mod 13. However, a negative number to an odd exponent, so this number will still be a negative number. This is 2 to the 90 is congruent to negative 3 to the 90 mod 13. Thus, this means that 2 to the 90 minus negative 3 to the 90, and 13 divides this number, which is 2 to the 90 plus 3 to the 90. And we prove this question by using congruences. Now let's look at the next one. Now for the next problem, show that 207 to the 23 minus 41 and to the 9 is congruent to 12 mod 100. So first let's look at 207 to the 23. So 207 to the 23, this is congruent to 7 to the 23 mod 100, because mod 100 is basically find the last 2 digits of a number. However, these 2 numbers does not affect the last 2 digits of the number. You can also prove this by, you know that 207 is congruent to 7 mod 100. You know that, right? 207 minus 7 equals to 200, and 100 divides 200. Thus, 207 to the 23 is congruent to 7 to the 23 mod 100. Now let's look at 7. So we are looking for an exponent that is more easily to solve the question. So we find that 7 to the 4th, that is equal to 2401, and this is much closer than 100, and 1 is more easy to solve the question. So we find the properties that 7 to the 4th is congruent to 1 mod 100. Now we can change 7 to the 23 as 7 to the 4th to the 5th times 7 cubed. And for this number, which is 7 to the 23, we have 7 to the 4th to the 5th times 7 to the 3. This is congruent to 1 to the 5th times 7 to the 3 mod 100. So basically that's A, that's B, and A is congruent to B mod 100. Then AC is congruent to BC mod 100, which is right here. So now we have switched that 7 to the 3, 7 cubed. We are looking for this number. It's congruent to some number mod 100. And this is just 343, so this is congruent to 43 mod 100. Now, let's look at this whole thing. 207 to the 23 minus 41. This is congruent to 43 minus 41, which is congruent to 2 mod 100. Thus, we have changed this whole number to 2 in congruences, which means that 207 to the 23 minus 4, let's just do it right here. So basically, we made this whole thing to the 9th power, and 2 is also need to have a 9th power on it. So 2 to the 9th, which is 512, and 512 is congruent to 12 mod 100. Thus, 207 to the 23 minus 41 to the 9th, 41 to the 9th is congruent to 2 to the 9th, which is congruent to 512, which is congruent to 12 mod 100. Thus, we prove this question. Next, we are finding the last digit of 523 to the 12 minus 84 to the 15. So first, let's look at 523 to the 12. So when we find the last digit, you can use mod 10, because we know that, like, for example, if we have a number 23 and we are finding the last digit, 23 is congruent to 3 mod 10. And this is just the last digit of 23. Thus, we have 523 to the 12, and this is congruent to 3 to the 12 mod 10. This is because just 523 is congruent to 3 mod 10, and we have 12 powers on each side. So now let's look at 3. So 3 squared equals to 9, and 3 cubed equals to 27, and 3 fourths equals 3 to the 4th equals to 81. This is 81 is congruent to 1 mod 10. Let's use 3 to the 4th to decompose it 3 to the tops. 3 to the tops equals to 3 to the 4th to the third, and this is congruent to 1 to the third. 1 cubed mod 10. Thus, we have 523 to the 12th is congruent to 1 mod 10. Now let's look at 84 to the 15. So for 84 to the 15, you have 84 to the 15 is congruent to 4 to the 15 mod 10. And 4 to the 15, 4 to the 15, which is equal to 4 to the 5th to the third, and 4 to the 5th equals to 1024, and this is congruent to 4 mod 10. Thus, we switch 4 to the 15th to 4 to the 4 cube mod 10, and this is much easier to find 4 to the 15th, and this is the magic of modular congruences. So 4 cube is equals to 64, which is 4. So 84 to the 15 is congruent to 4 mod 10. Thus, we have 523 to the 12th minus 84 to the 15. This is congruent to 1 minus 4 mod 10. However, 1 minus 4, which is -3. So -3 is basically congruent to 7 mod 10, because -3 minus 7, this is equals to -10, and -10 is divisible by 10. Now let's look at the last question. Prove the congruences 13 to the 888 is congruent to 1 mod 7, and 2 to the 341 is congruent to 2 mod 341. So for the first one, we have 7 times 2 equals to 14, and 14 is equals to 13 plus 1. Thus, we have 13 is congruent to -1 mod 7. So we have power of 888 on both sides. Then 13 to the 888 is congruent to -1 to the power of 888 mod 7. And that's just one. So we have proved the first one. Now let's look at the next one. We have 341 times 3 equals to 1023, and that's equals to 1024 minus 1, which is 2 to the 10 minus 1. Thus, we have 2 to the 10 is congruent to 1 mod 341. So you have power of 34 on both sides, then 2 to the 340 is congruent to 1 mod 341, and we times 2 on both sides. Thus, 2 to the 341 is congruent to 2 mod 341. And this is all of the modular congruences I have. If you have any questions, please contact my email, and see you next time.